So in this whole documentary, it's kind of like a documentary, except this is like a mixture of a lecture and a documentary. So the first episode we saw the dream of a perfect proof. We saw the Aristotle, the OG, who did all the who laid the foundations or discovered the foundations of the what now is evolved to be called as logic. We saw Leibniz with a few 2000 years later, and then we saw the modern logic with Frege, and then we saw Russell and Frege fighting, and then we saw Hilbert's proof theory, and then we saw how the guy, so how a young Austrian tried to challenge the great Russell with his uh, by finding flaws in the Russell's solutions to the paradox. So that's what we will be discussing now. And so in the last episode, basically, I said I would answer how to solve a hit paradox. We will look into that now. And what was exactly Wittgenstein's attack on Russell? So uh, uh, his attacks were that um, uh, he says that to Russell that you are just misusing language. You cannot just say that language is broke. The language itself should have some meaning. Otherwise, it doesn't have anything. So he says the paradox isn't mathematical, it's linguistic. Russell treats language mistake as a logical problem, but Wittgenstein consensus bad sentences shouldn't be fixed, they should be shown meaningless. And that the type theory is a band aid. And he introduces his type theory. And the fact that logic can describe its own structure. In the Tractatus Logico Philosophicus, uh, written by Wittgenstein himself, he says that logic shows itself, it cannot be stated. Yep, so this is where we had left. So, in the and Wittgenstein also said that the formal logic is just one language game, and Russell overestimates logic's role in philosophy. So that's what I said. And Russell just basically found flaws in the language. We will be looking at that into more detail later now. And coming to the fifth chapter, the Gödel's incompleteness theorem. So now we're in part two. The, this is where the dream shatters. The dream of a perfect proof that we left in the last episode. This is where it shatters, and we will see why and Gödel and how Gödel is the culprit of this. Well, Gödel is one of the legendary figures. He shattered the dream of the perfect proof. The idea of a perfect proof itself was not that great. Why there are some fundamental flaws in mathematics itself, in the things that we ground everything itself. So let's go to this now. When Gödel was 24 and trying to expand his results to cover arithmetic, he ended up with a thoroughly unexpected result. He found out Gödel's incompleteness theorem. Now, what does it say? Well, it says that any formal system that is inconsistent. Well, Gödel's incompleteness theorem again has two parts. So, it says that uh, the first incompleteness theorem says that any formal system that is inconsistent and is powerful enough to do arithmetic contains truth statements that cannot be proven within the system. So, contains go back. Truth can be proven. And the second says that, so this is within the system. So second says that such a system itself cannot prove its own consistency. So This is within system, and system itself can be proven of its consistency. So, so these fundamental flaws, the fact that a system is incomplete in a sense that the truth inside of it cannot be proven, and the system itself can be proven either. This is the what forms the Gödel's incompleteness theorem. So Gödel says, I finally arrived at Princeton University, where I teamed up with Albert Einstein and Oscar Morgenstern to form what was, if I do say myself, the most brilliant mathematics department in America. So he's right on that. And Gödel's ingenious proofs mark the start of modern mathematical logic, and his work has dictated the course of logic up to the present day. And the connections to proof theory. Now, the modern logic may be divided into three connected projects. There is a mathematical logic, symbolic logic, and philosophical logic. Mathematical logic continues the project of bringing together mathematics and set theory. With it, mathematicians hope to unify different mathematical fields by discovering their common properties. Now, philosophical logic tries to apply logic to the actual concepts, the real world concepts, instead of pure symbols. So, and symbolic logic is the pure inquiry into the manipulation of symbols that do not have correspond to anything in the real world. And so you kind of see that these are all kind of lie in a spectrum or in a set, and at the center of all these three lies the proof theory. Now, proof theory contains a variety of methods to show what logically follows from a logical sentence or formula, a string of symbols connected by bits and logical syntax. It does this by giving rigid definitions of bits of logical syntax. Now, the logical syntax will affect the truth of the truth of a statement. So, I define pieces of logical syntax in the terms of truth and falsity. So, enter Wittgenstein's truth tables. Now, Wittgenstein first devised these truth tables that we kind of very popular now that we use in the logic gates and everything. So, so I mean, as you can see, like P represents the clouds and Q represents raining. And if cloud is if the fact that it's cloudy is true, then it could rain. If the fact that if the cloudy is false, then it could either rain or it could not. So with this, you can say that uh, it can only rain when both it's cloudy and rainy. So you can only say it's raining when it's both true. So you know what truth table says. So it's just convenient way of representing stuff. And he also introduced this connective called as not. It does not, which is a negation of the statement. So if P is the statement, then its negation will be the exact opposite of it. Discovering tautologies. Now, tautology means like similar words. It's the study of similar words. Taut in Greek literally stands to the same. So ology, logic is the study of similar words. So literally, uh, A is the same as saying not A or not A. So if not A exists, then A is equal to not A. So and that's tautology. So it's not much to be discussed there, especially not in this big picture of logic. The logic gates of logic digital electronics. So now these logic truth tables are widely used in the digital electronics logic gates, as you might re- recall if you have studied engineering or even if you have studied mathematics in your higher school. And the AND gate, the OR gates, these logic gates form the basis of everything you see. They form the basis of computers. They form the basis of the transistors. So the logic gates and transistors act kind of like the transformers that are present in these LLMs, and maybe even more fundamental than the idea of transformer, because transformer is just one method on which it's based on. It's not the most fundamental thing in an LLM. So these logic bits are literally the most fundamental things, and there is not more fundamental than that. It would be just atoms. So a transformer and the logic gate, and so here we have Alan Turing saying that the heart of a vending machine is no more complicated than a number of AND gates strung together. Just look at this simple diagram. He says, well, he basically, you can say, kind of like the Alan Turing is the father of the modern artificial intelligence, or okay, not modern artificial intelligence, but he laid the basis of all the artificial intelligence that we see today. And Turing and the Enigma code. So I would highly encourage anybody seeing this to actually go and check out the movie of Alan Turing. The I forgot the name. So starring Benedict Cumberbatch, and it's a great movie. Euclid's axiomatic method. Now, anybody who has studied geometry, even in the primary school, you will have encountered the Euclid's axioms and postulates. Axioms are the fundamental truths which cannot be proven. They're taken as given. They're taken as they are the proof, and the simple five axioms is what forms the basis to build other tons of theorems and postulates and other stuff. So the kind of like the axioms kind of work like a tooth pump. So he says, I chose the most self-evident axioms I could, as the most certain as we are of the truth of the axioms. The more certain we can be of the statements derived from them. So Newton says, I developed my logic from Euclid's system based on four axioms that became part of the canon for all later developments. So okay, that's not Newton, that's Leibniz. Leibniz proof method. The first axiom is Leibniz's famous law of identity. It says everything is identical with itself, and the law of non-contradiction, which says obviously the contradiction of something is not equal to that thing, which means the contradiction of that thing is equal to that thing. And the law of excluded middle says that every statement is either true or false. Can be both. The law of substitution says that A is B and B is C, then A is C. You can substitute them. And this is basically the basis of the reductio method, reductio ad absurdum. Now, what causes contradiction is that you can somehow hack your way into proving really absurd statements using these laws. So you can prove like 1 plus 1 equals 5 or something like that. So, but again, the fact that you can do that is probably has a flaw somewhere there with something, and that's why that's where Russell comes in. Russell says that language itself is wrong. The language has flaws in it, and to which, as we saw, Wittgenstein says that language is right. Language can be meaningless. It's not a flaw in that language. So that's the high level view of what the Russell and the Wittgenstein's whatever he did, and the sensitivity to grammar. So Russell says, for precisely this reason, I reintroduced Aristotle's distinction between subject and predicate, objects, and the things we say about them into my logic. Not the actual words, but the structure of sentences becomes mirrored in logical symbols. The predicate calculus, or the propositional logic. Um, so this is what was invented by Russell, and so here we just use the pure symbols. So and there is a like this whole thing. Socrates. So no human is immortal. We can we can represent it like this. So this H stands for the human. So there's there's no there's no statement. There's no person like which belongs to there's a mortality and human. So Socrates is human. Socrates is mortal. So it's a formulaic, symbolic, computer-like way to not. I mean, can say the computer-like. So this is the formulaic representation, symbolic representation of logic. This is much more modular. So this is much more easier to calculate complex stuff. This is like um, turning this into maths, turning the logic into mathematics, which means you can play around it with much more consistency for and solve much bigger problems. And basically, logic becomes scalable and highly useful all of a sudden. Now, enter Tarski's semantics, the model theoretic semantics, first invented by Tarski. So now Tarski will come up ahead just in a while, but let's just see what Russell and Turing and Socrates has to say here. So Turing says, Russell says that the models allow us to attach meaning to logical formulae and so investigate the truth of particular statements relative to a given situation. This is called model theoretic semantics. Without it, we cannot do. All we can do is show that argument is valid. That if px then qx. So we need kind of a higher level than just these symbolic representations. This is fine. This is scalable, but we need something higher level of abstraction than just this. That's where the model comes in. That's where the semantics comes in, not just the symbols throwing around. So these are just like words. These are just a piece of words, or you can say like these are just one layer of abstraction. The another layer of abstraction, if you like, if you want to add, would be that would be models. That would be semantics. So Turing says this is a great idea because once the model becomes large and complicated enough, you can apply it to thought itself. That would be great help in understanding a given mind and constructing machines that can emulate it. So in fact, we do use lots of semantics, lots of models. This kind of higher level hierarchy of uh, systems is exactly how we build anything. This hierarchy and uh, abstraction and layers of complexity to make it scalable and working. This is the basis of every single subject in the world. This is the basis. This is how engineering is done. This is how any subject is divided and done. So now Hilbert's recursion model. So now enter Hilbert again. So Hilbert's recursion model. So this is kind of an important topic, although we haven't i- given it a dedicated chapter because it comes under task case semantics. So let's see. Precisely, it's the tools developed by Hilbert in his work on the foundations of mathematics. So it was actually Hilbert who did it. Hilbert wanted a mathematical version of proof theory, a way to prove mathematical statements from within mathematics. This name proof theory is actually Hilbert's, like I said already. So it says to this idea of recursion. Now remember this idea of recursion. Recursion applies everywhere. Recursion applies in if you anybody has Gödel, Escher batch. So the fact that life itself is recursive is what the idea is expressed in this famous book, Gödel, Escher batch. This is one of the most, if not the most complicated book ever written, and it's one of the most profound books as well. It's I mean, I can't say it's up there with Bible, but Bible or any other holy book, but it is highly profound. Okay, it describes how life came from mathematics and logic, uh, not logic, but how life came from meaningless. So how does something that is meaningless symbols, how do they acquire meaning? That's through recursion. That is through recursion. The fact that the idea itself, the symbol itself, has a lot of it recurs a lot, which means any idea that is strong. Let's say the idea of good, the idea of bad, the idea of good is way more abstract. It's way more meta, but let's take it anyway. Let's take the idea of God. The idea of God is so famous because it recurs a lot. It's highly recursive. and even though it's meaningless, it acquires a meaning because of that recursion. So I'm someone who is highly interested in these topics, like this book exactly, and other topics that it discusses. G stands for Gödel. Okay, the Gödel that we just saw, Gödel's incompleteness theorem that we just saw, and that's where he says he talks about all this, and yeah. So we will discuss about the GSB book perhaps in some later video. But if anybody is watching this, hey, anyway, so uh, Hilbert's had a view of mathematics that he called formalism, the idea that things mathematics talks about are nothing but symbols. These symbols are by themselves meaningless. You know how you know about them when you know how to manipulate them. He gave recursive rules to explain their possible interactions. The most famous mathematical entity is the number. All positive whole numbers can be constructed from two simple rules. One is a number, and any number plus one is a number. This most simple rule he uses. So this is perhaps again like the first model or a theoretic semantics. We use an example here. So like a sentence called we use one predicate and four names. We use these both to compose lots of statements like Homo erectus evolved from Homo into Homo sapiens, and there is a semantics involved here. So the fact that you can only go upwards in direction, that is the semantic rule here. So the second rule, the first rule shows how to build a well-formed formula out of sequence name predicate name. So this is the first rule. The second rule says that how to build a new well-formed formula out of a sentence that already exists and in addition to the sequence which. So this is one rule. The second rule, like a name predicate name, and we can also use sentence which predicate name. So this is one example of one model, and finite rules for infinite production. So, but just by using simple some finite rules, you can compose infinite statements. So all you need to know about the word and, if you know and, you can compose anything. So the American philosopher Donald Davidson has suggested that we can apply this idea to English and every other natural language, filling in the gaps with the semantic model. So that's the semantic model. Through coming to proof theory and formal language, Davidson encourages us to think of all adjectives, adverbs, and prepositions as predicates strung together. This contrasts with Russell's analysis of those linguistic terms. So here is Russell and Davidson both skating. So Russell says, I said that I went skiing with a friend is a single predicate that says something about two subjects. A predicate like went skiing with only makes sense if there are two subjects attached. And Davidson says, but Russell, how can you account for the fact that I went skiing with a friend actually entails I went skiing? Russell says, I can't because in proof theory there is no way to account for the entailment from a two plus predicate to a one plus predicate. Proof theory lacks the relevant semantic machinery. Not only that, but in English we could extend our account indefinitely. For example, I went skiing with a friend in the winter in the Alps where it is cold. On your account yourself, we need a new predicate for each subsequent addition. This means we would need a potential infinity of predicates, and that is unlearnable. So if we construct the sentences my way with a string of different predicates linked by conjunctions, then a simple recursive rule can account for all of them. So at root, Davidson is trying to understand English as a formal language. To do this, he needs a way of deciding under what conditions sentences of English are true. Davidson adopted an account of truth in formal languages developed by Berkeley colleagues Alfred Tarski. Tarski developed a distinction between the formal language and the language used to speak about the formal language, the meta language. Tarski's truth conditions. Tarski, the inventor of the, the inventor of the model theoretic semantics, just semantics in simple words. He provided a set of conditions that allow us to say when a sentence of the formal language is under study is true. This result is startlingly simple. So Basically, it says that any sentence, every sentence is true in the meta language. So there is a meta language. Meta language. Any sentence like French, or English, or Canada, so they all come under. So you need to go into meta language and then make that sentence truth and verify the truth of the sentence. Formal semantics and practice. The great practical advantage of formal semantics lies in the ability to build machines that respond to formally defined language. All computers are such machineries. So let's take a quick ad break. Just kidding. There's no ads in here. I mean, I don't know where the ads are coming. Uh, so where were we? Just quick recap. So what were we in? So we were in the Gödel's incompleteness theorem, where we saw how Gödel crushed the dream of a perfect proof of Hilbert's was crushed. That's what we saw in the part one. And after that, we saw Wittgenstein's truth tables, the truth tables that form the basis of logic gates and the logic used in all the computers. Then we saw Turing's Enigma code, and then we saw the predicate calculus by Russell, and we're seeing Tarski's semantics. So the study of semantics and how the models. So here we are seeing another example. This is one example of a model. We use this model. This is again only finite statements to construct infinite number of soap operas. So and prologue to an AI soap opera. Prologue is a programming language invented by I'm not sure the name, but it was a language specifically created to uh, build the AI, basically to go deeper into AI and do research in artificial intelligence. So Prologue is so while all computer languages are formal languages, some show their true nature more blatantly than others. Within the most computer languages, the vocabulary and grammar are preset, but languages like Prolog allow computer to develop its own programming. So this is, so like I said, this is made for AI. Prolog is a language for AI, and the motivation comes from the idea that machines could have skills of learning, self-correction, communication. So this again, Turing forms the basis of these ideas. The representation learning, like I explained in my video dedicated on deep learning and machine learning and artificial intelligence. This is the basis. This is the higher subject. This ML and AI both come inside of this bigger subject called representation learning. How can you represent the entire world in your device? If you're able to represent it, at least a model of it, then it can navigate through it. So machine learning is basically trying to represent the world by learning it. So this models enable to represent. So models, the semantics enable you to do representation learning. And Turing had a recipe for AI, a model with a vocabulary rich enough to represent the real world is what we need. And also we need that this model can then be used to build a picture of the world, the representation, the main thing. And you might find a dash of self-learning helpful here. Now we need to put together the input and output devices. So first we need a model with a vocabulary rich enough to represent the real world. And we need the picture of the world. It needs to have self-learning. And you need to put input and output devices. That is the basis of AI. And he used this idea in his Enigma machine. And now comes the problem of paradoxes. Well, Russell discovered a paradox in my system of logic, says Frege. It made everyone, even me, reject the system. The paradox he discovered was an unavoidable contradiction built into the system. Frege became an object lesson for logicians and who have been trying to avoid paradoxes ever since. So this sentence is false. If you say like that, it is false, isn't it? Can paradoxes be avoided? Can they be? So Russell's being his theory of types. Again, this is an answer to the Gödel's incompleteness. This is an answer to the Russell's paradox. Okay. And he comes forth with the theory of types. He says that the uh, the the paradox in the Russell's paradox of the sets, the fact that a set cannot be a part of itself. How you solve it is by using theory of types. You say that sets should come in hierarchy, and a set cannot be a part of another set which is lower down the hierarchy. So I'm kind of using simpler words here. So let me. So because objects are arranged in hierarchical types, a set can only contain objects of a lower type. So a set cannot be a part of itself because it is not a lower type. It is on its same level. So that is the theory of types that he discovered. So this leads to a familiar pattern. If it is a member of itself, then it's not a member of itself. So let's just come with the complicated logic machinery to tackle this problem. This is the theory of types and all that. And Tarski's solution to the lie. Tarski thought that his own distinction between the language and the study and the meta language could neatly take care of the liar because it's true and it's false predicates of the meta language. A sentence cannot contain its own truth predicate. This sentence is false. It's no more part of the predicate language and more is Blanche is part of English. So a sentence cannot contain its own truth predicate. So the unexercised paradox, just as liar appeared to be a problem for Russell. So paradox like the next sentence is false, last sentence is true is problematic for Tarski. One sentence seemed to belong to both the meta language and to the meta language for the meta language. So take a look at this heterological thing. So this word itself, heterological, is a paradox, right? So it also says the problem for the simple theory of types is that the liar has two predicates of different types. The liar is basically this is lying itself, the liar paradox. So a situation it cannot cope with. I did find a way to cope this with the problem, but only at the cost of making my system even more unwieldy. Here comes Willard Van Orman Coin. Russell's new system prevented so many crossovers between the types that it became impossible to prove even the elementary propositions of set theory using that system. So again, now let's revisit the sixth chapter, that is Gödel's incompleteness theorem. So the most influential of the modern self-referential paradoxes is Gödel's second incompleteness theorem, the fact that the system cannot be proven itself to be true or consistent. It was first published in 1931. Few people could understand it. This does not mean that the ideas behind it are particularly hard. It just had huge impact on science, mathematics, and philosophy. Gödel came up with the ingenious idea of encoding statements of logic and mathematics as numbers. He assigned every symbol in Russell's logic as a number. So basically, if you have to say like something like this, you represent it as a string of numbers 1 1 2 2 1 1 1 2. So this kind of helps for consistency. So using this method, I showed that a particular number would correspond to a formula in Russell's full system that says this formula is unprovable. Once we have arrived at this formula, we can go one of two ways. First, suppose that sentence is true. We have a true statement in Russell's logic that cannot be proven. This means that Russell's logic is incomplete. Alternatively, if a sentence is false, it means that it is provable, but then it is a false statement provable in Russell's logic, so it is incoherent. So, what are the consequences of this? Neither of these suggestions is very appealing to Russell or Hilbert, so who wanted to construct a system that will produce all and only true sentences of mathematics. Because obviously, this produces a lot of un- untrue sentences. Just a random string of numbers can point out to really uh, false statement. So Gödel says, I showed that the basic branches of mathematics may be formalized by a set of axioms in accordance with Hilbert's program, but the conclusions of my theorem applied to them as well. So either basic arithmetic is incomplete or it is incoherent. Either one or true calculation cannot be proven, or one false one can. And it's not all bad news for the everyday practice of mathematicians as long as they show that the systems are consistent at the price of being incomplete. They can continue to produce by far the great majority of mathematical sciences. Whilst my now Hilbert says, whilst my program was devastated, my method continued to be of use in formalizing and axiomatizing new branches of mathematics. I myself devised a mathematical system to deal with the bizarre realm of quantum particles, which they now call Hilbert spaces. Wow, so he's also part of the quantum mechanics. The halting problem. The Gödel's theorem shows us something very similar when applied to computation. Using Gödel's numbering system, every form of mathematical proof can be transformed into a relatively simple numerical calculation. So every true formula there corresponds to a particular number. This means that there is a formula that cannot be proven. If there is a formula that can be proven, then there is a number that can be calculated. So Turing says computers are machines that simulate numerical calculations. It is basically mind numbering is a technique that allows them to run programs within formal logic. So this numbering thing means that Gödel's incompleteness theorem applies to computers, and uncomputable numbers correspond in a way that programs that will never give a result. Gödel's incompleteness theorem means that there cannot be programs using a finite number of steps to check any program to see whether it will reach a conclusion or not. This has become known as the halting problem. Such a program would be equivalent to a system in which you could consistently compute out numbers, and that is an impossibility. So if you halt to a number that cannot be a number, then basically it means that the formula that this number corresponds to is false. The limit of Gödel's proof. Despite its wide-ranging ramifications, there are certain things that Gödel's proof cannot do. It does not absolutely guarantee that we could not use Hilbert's methods to prove the consistency and completeness of arithmetic. Only that such a proof is not capable of being represented within arithmetic. This is true, but nobody to date knows what such a proof would look like, let alone how to construct one. It cannot be used to say, as some have tried, that mysterious intuition must replace cogent proof. Nor is it to prove that there is an inherent limits to human reasoning, since no one knows if human reasoning falls under Hilbert's rules. Now, it doesn't mean that we have no hope of explaining thought in physical terms, but it does cast doubt on possibility of any system of rules that formalize any possible sentence. Gödel's incompleteness theorem has ever made it into first year undergraduate ethics lectures. That's how profound it is. Zeno's movement paradox. Now, there is a Zeno's movement paradox. We'll skip this. This is not that profound, I guess. Maybe just not profound in this. Maybe not profound to me at least. So there's the same infinite sum paradox. So let's go to a convergence on limits. When Newton and Leibniz discovered almost simultaneously what was often the sum of a positive number of integers is not infinite. A sum of infinite calculations have the property of converging on limits, which is to say, each subsequent addition we get ever closer to a particular number. So both basically arrived at calculus, each on their own method, which is incredible. So there's another famous non-self-referential paradox, the sorites or the heap paradox, and it relies on the fact that some words in our language like heap are vague. What exactly is a heap? How many particles are a heap? So I would say this like this degree. Okay, so there's a I would solve this thing. There's a everything lies on a spectrum of degrees. Okay, maybe not everything, but at least like there's a most things. So okay, so and this heap exactly can only start from when it's at least like I don't know, like 100 particles. We can give it like that, and so we can say it like that. So what difference can a single grain of sand make? If I were to remove another grain of sand, would it be also a heap? Of course, another. So this is a heap paradox. Well, philosophers got very excited about combining sets and logic in order to analyze the language. One common idea is the predicates of our language correspond to sets, and the predicate is a heap, corresponds to set of all heaps. What the Sorites tell us is that there will always be a questionable case about whether something is a heap. If we do not have a solution, then the whole attempt becomes questionable. Law of identity and the law of non-contradiction. So, undermining logic. Apart from threatening the attempt to use sets to analyze predicates of a language, the Sorites paradox throws into doubt the ability of propositional and predicate calculus to describe the way the world is. Law of identity and the law of non-contradiction are two fundamental axioms of our systems of logic. The Sorites paradox challenges both. Again, the solution would be to just assign like a degree after which it can be called as a heap, and of course this means that it can be used in logic as scalable as the mathematics that we know of. So that's what that's what I arrived at, isn't it? The solution I was talking about it basically is fuzzy logic, and so this undermines logic, the fiction of vague words. Again, the vague words. There's no degree assigned here. So I did arrive at the same conclusion as the fuzzy logic. That's why we need fuzzy logic. So words can be vague, and what do words mean exactly? So what is a heap? After what can it be called as a heap? That's where comes the fuzzy logic. So till now we're seeing about in part one we saw to recap again. In part one we saw the dream of a perfect proof from Aristotle to Hilbert. They're trying to construct the perfect proof, but they failed because Gödel came and, like we saw, he proved that a perfect proof cannot exist. A perfect system cannot exist because there are the systems itself. Any system, no system is complete. All systems are incomplete. So he proved that, and he shattered the dream of a perfect proof. And then comes the final part. The final part would be the birth of the machine, which we will see in the next video. Birth of the machine. So here we will see Turing and all the modern logic that has led to what the future looks like, what the present looks like, which is kind of futuristic. If you see where everything is going, it's already futuristic. So the dream shatters. There's come truth tables. There comes Tasky, and with his semantics, he elevates he makes the logic more scalable with his semantics model, and the fuzzy logic is where the birth of the machine begins. All the fuzzy logic is not used in your machines. I mean, at the most in transistors, the idea of fuzzy logic is not used as much as the simple logic itself. The truth tables are more used there, but the fuzzy logic is used much more. It is used in AI, and it forms one of the fundamentals nonetheless, even if it's not used directly. and the logic of science by Popper. We'll see next, and Popper and all the modern logic. So the birth of the machine again. We will be studying like how AI is itself is built. However, we will look at that as well, but we'll see mostly the logic and what led to it. So as this entire series is based on logic itself. So these again, first chapter was the dream of perfect proof, and then we saw the dream shattered, and where we were left was, so here it was from Aristotle to Hilbert, and this was from Gödel to was the guy who was the guy fuzzy logic. So from we just left from from Gödel to again Hegel from the fuzzy logic. There's no exact person here basically. So nonetheless, we will see the next part, the birth of final machine, the birth of a machine in the next